Another important thing that graphene, like again, it's all based around this notion that graphene's tunable, that graphene's electrical conductivity can be tuned. So another important thing is to design backscattered modulators. So backscattered modulators are modulators that are self-powered, that are powered from the baseband signal or the signal that is falling onto the circuit, so onto the modulator itself. So you have a signal that is directed from an antenna to a matching network, and then it falls on the modulator. And the modulator changes the signal based on the environmental impacts or like a signal that you put on the modulator. It changes the response in a certain way that can carry an information regarding any information that you want to transmit. So it could be, for example, in the placement of wireless sensor nodes in areas where you cannot have physical access, or physical access is hard to have. For example, in order to avoid forest fires, or if you want to get access to information regarding temperature and humidity and things like that. So again, graphene is an integral part of the modulator itself, or of certain areas of the modulator, in order to cause this effect, in order to vary somehow the conductivity that would carry this information back. The important aspect of these wireless sensor nodes are that they are backscattered, which means that they do not need power in order to operate. So all the power that they will get is from the baseband signal, or of the signal that they are getting. So this is one important aspect. Now, to make them, since there is a push for ecological materials, therefore we try to design it completely, let's say, organic or biodegradable, sensor. So this was designed on paper. So the combination of paper and silver are both not damaging for the environment. Graphene itself is based on carbon, which is also environmentally friendly. So the idea is to design a sensor, a wireless sensor node, that is entirely biodegradable and not damaging to the environment. The key point here was how to make paper substrates that are stable, and if they change their response, we should know. So in order to do this, we need to get accurate information about different aspects of paper, for example, complex permittivity. So typical information that we need about any substrate on which we are designing our circuit or our radio frequency component. So in order to do, we did analyze based on the variation of humidity, which is a key factor, because when there is water that is penetrating into into cellulose, it could really alter the response of the sensor itself. So this was also stabilized with, there are different techniques which we could use in order to glaze the paper or do something to stabilize this. So in the end, we have a stable, fully biodegradable sensor based on paper that could carry information regarding humidity and temperature. Again, something regarding electromagnetic interference and shielding effectiveness is that the GrInShield project is all about how to block signals and how to avoid electromagnetic waves in order to reach certain areas, in order to protect equipment or humans, for example. So in order to do that, it's really important to highlight the importance of the dissipation of microwaves in a surface or in a shield, for example. So we, in most of the cases, what we want is to increase the dissipation of a microwave signal. It means that when an electromagnetic wave falls on a surface, we do not want it to be reflected back, but rather to be dissipated in this surface. And here I have demonstrated that that when you are designing an attenuator, which is a device which will, let's say, kill or reduce the transmission of microwaves in a circuit, we can see here that that the total attenuation or the total attenuation of the signal will be composed mostly of the dissipative part of the signal. So it means that when an electromagnetic signal will fall onto a surface, most of it dissipates. So 5 dB out of 35 dB is what is reflected back, and most of the signal will be dissipated in our shield if it is composed of graphene. So very quickly now, how do we, now we know the importance and how to design different electronic circuits and different objects with graphene. It's really important in order to know how to characterize, how do we know the exact electrical properties of graphene. In order to do this, we have setup which is called a scanning microwave microscopy. The special point of the setup that we have is that it is combining many different microscopy techniques all in one instrument. So we have a scanning electron microscope, we have an atomic force microscope, a scanning microwave microscope, all in one setup. So it gives us the possibility to study one material from many different aspects. So we can visualize it optically, we can visualize it by using scanning electron microscopy, we can in the same time study the conductivity of graphene or different materials all in this one setup. This enables us to know precisely how the conductivity of graphene varies with the application of an electric field and things like that. So this is one example of what we could do. So we are studying the topography, the magnitude, and the phase of a microwave signal that is falling, that is going out from atomic force microscopy tip onto a substrate. So I will just quickly finish my talk with enzymatic, or let's say concentration of enzyme detection by using radio frequency signal. So what happens is that if we have functionalized surface in which could attach only certain molecules to its surface, it could give us the possibility in order to study the impact, the electrical impact of only that particular molecule, and then transfer it to a radio frequency signal which we could read on a sensor. So in this case what happens is that only glucose is attaching to a surface because the surface is functionalized for glucose oxidase, and we could tell how many molecules, or let's say the concentration of the molecules that the solution that we are depositing on the surface has, and then we can correlate this into the radio frequency signal which we can read on our sensor. So thank you very much for bearing with me, and we are open for collaboration or any talk or anything that you would like to share. So this is some information about me, our group, and where we are located. Thank you very much.
You're open to questions. Sure.
Because I asked before and I was told that there are no questions. Anyway, yeah, you can. Yeah, sure. Yeah, we have. So there's an article which we published in which we demonstrated that we could detect really low concentration of glucose down to like 5 milligram per deciliter. We have many working prototypes, but we do not have an object itself, like a device. Yeah, these are prototypes. Yeah. It is more sensitive, yes, because the normal concentration of glucose when you are fasting is like, let's say the lowest could be 70 or 80 milligram per deciliter. And if we could detect down to 5 milligram per deciliter. So the idea here is to base the sensor not on blood glucose concentration, because concentration of glucose in blood are higher than concentration of glucose in other bodily fluids like sweat, saliva, tears, and others. So the idea is to design something that could detect really, really low concentrations, which could target future devices that could be able to detect extremely low concentrations, so we could make a device that makes it possible for us to detect really, really low concentration based on other bodily fluids other than blood. That's the idea. Thank you for the question. Any more questions? The thing is that for the FPGA design, it's for designing controllers that would make it possible. So the FPGAs are not designed based on graphene. Graphene is sorry, again, can you repeat? So the dimension, so one of another most interesting property of graphene is that it's scalable. So if you can keep the aspect ratio constant, then you can reduce. So right now this is 5 microns by 5 microns, but we can observe really like even on a nanometric scale the properties of graphene. That's the whole idea. So we study material on an extremely smaller scale, and then we can project how it will behave on a bigger scale. Generally, we are limited not by the smaller size, but by the bigger size. So the scanning that we are doing can do it by up to like 5 microns by 5 microns. The lowest that we can scan is like 2 nanometers, 2 or 3 nanometers. So that's the and the devices themselves, they could be bigger. Like, you know, we study characterization at an extremely small scale, and then we project how it will behave on a bigger scale. Because if you are talking about frequency selective surfaces and things, they are on centimeters and millimeters and centimeters dimension. No, this is not a processor. This is a totally different thing. So this is radio frequency surfaces, nothing to do with processing. Of course, there are transistors based on graphene as well. So there's also studies that are going on in that direction. But what we are focusing on is to study graphene locally and then make radio frequency integrated circuits, for example, or microwave surfaces or devices that are really exploiting microwaves and radio frequency signals in order to make, let's say, yeah. But the FPGAs that I mentioned, we are using them. They are standard FPGA off the market, used only for designing control systems that would give us the possibility to study them, to study different materials or graphene or whatever. You're welcome. Thank you.